Hey everybody, let's give this problem a try. So it looks like we have a disk. So I already grabbed this from the appendix for a disk, the moment of inertia. Okay, so it's turning and we press an X against it with some radial force. I'm just going to draw. So here's our grindstone. And then if I press something against the disk this way, then Newton's third law, there should be an equal and opposite force. Right, so there's going to be a normal force on the grindstone, normal to the surface. So normal to the surface like this. And then let's say it's rotating whichever, like, say it's going clockwise. Then there's going to be a friction force opposing that motion, right? So this way, friction, kinetic friction. And then the grindstone has weight. So it has weight, the weight of the grindstone. Okay, that looks like pretty much it. All right, so let's write Newton's law for rotation. Let's sum torque about somewhere. So where do you want to sum torque? About over here, over here, over here, over here. This is a good idea. Because about this point, the torque from the normal force is 0. The torque from the friction is 0. There would be torque from the weight. So that's a pretty good choice. Or we can sum the torque about the axis of rotation of that grindstone. It's over here. Why don't we do that? So let's sum torque about that axis of rotation. And then let's pick a direction. So let's say Z. Say if X is this way and Y is this way, which way is Z? So practice your right-hand rule. It'll be into the page, right? Which is this way. So let's call that positive Z, going into the page. Okay, so there's going to be torque from this force. There wouldn't be torque from the normal force because it's aligned with the axis of rotation. So there's torque, and then it would be in the negative Z direction, minus that radius times the kinetic friction. And I guess that's it. That's it. Equals I alpha. Okay. And then see this friction is coefficient of friction times normal force. Okay, and then I brought this from the appendix for a reason right there. Okay. So let's put all of that together. Let me just rewrite it. Okay, so minus R friction mu k times n equals I, which is from over here, 1/2 mr squared alpha. Okay, and what are we trying to solve for? We're trying to solve for the angular acceleration. Okay, let's check. We know pretty much all of this. Here's our unknown. So let's just move this over here in the denominator. So let me just solve for alpha is minus R mu k n over 1/2 mr squared. Okay, so things cancel. There's r over r squared. So let me get rid of that. Instead of 1/2, let me just put the 2 in the numerator. Okay, and there we go. There's the answer. Okay, so this is your answer. So remember, don't plug in numbers until you're done here. Now we can plug in numbers. So whatever the values are, just punch it in the calculator. So mu k was, let me just write on the line below it, minus 2 times mu k is, where is it? Oh, there, 0.2. The normal force was given 20 newtons over here. 20 newtons over the mass, which is 90 kilograms. And the radius was given 0.34. Okay, now you can plug this in the calculator. Okay, plug in a calculator. Whatever the calculator tells you. Done. Okay, part B. How many turns will the stone make before coming to rest? Okay, so that's a kinematics question, right? So of all the formulas you know from kinematics, wait, let me make a copy of this. Okay, so all the formulas you know from kinematics, what should we use? You know, stuff like this. Kinematics for constant acceleration, right? You know, this one. If you solve this for t and plug it in there, then you get this one. Okay, so it boils down to what do we know and what do we not know. We just solve for the angular acceleration here, radians per second squared, right? Just punch in the calculator. It'll be negative something radians per second squared. Okay, and then let's take a look. We are starting at 90 RPM, and then we want it to come to rest. Okay, so, and we already know the angular acceleration, alpha. So I have my eye on this one right here. Right, because the initial angular velocity, we know 90 RPM. The final, 0. Alpha, we just solved for it. And how many turns? That's this. Okay, so let's solve. Okay, so omega squared minus omega naught squared over 2 alpha. But this is 0. Okay, so it's negative omega naught, which is 90 RPM. So already I have, that is giving me some stress here. Because revolutions per minute, I don't like those units, right? So we got 2 pi radians per revolution, and 1 minute is 60 seconds, right? If you do this, see how minutes cancel, revolution. So then you would have something radians per second, SI units, right? So that is better, right? So that's omega squared over 2, and then alpha, which is, you just have it from over here, right? All this goes here, there. And then just plug in those numbers. Or if you solved enough, you kept enough digits here, you can just plug in that number here. Okay, and then this will be, well, actually, this is going to be something radians. So just how many turns is that? So you would have to convert back to revolutions, but I wanted to keep it in SI units. I would never ask, so I would ask things in SI units, right? So there are 2 pi radians is 1 revolution, which is a turn, right? So that's the conversion factor. Okay, I hope that's helpful. I'll see you on the next video.